So we represent compounds with chemical formulas. Remember, a compound has a specific ratio, proportion of the different elements. And the formula is a shorthand way of indicating which elements are present and the relative numbers of them. And we can write formulas for molecules or for ionic compounds. We use a subscript. It's a lower number following the element symbol to indicate how many atoms of that element are present. So if we look at this formula for water, H2O. H2 tells me that there are 2 hydrogen atoms, and the O tells me there's 1 oxygen atom. We don't write H2O1 because the 1 really isn't necessary. If there weren't any oxygens, we wouldn't write the O, and if there was more than 1, we'd write whatever number that is. So we just leave the 1s out, makes it simpler. Sodium chloride is represented as NaCl. This is the lowest ratio of sodium to chloride ions. There's 1 of each. Carbon tetrachloride, CCl4. 1 carbon atom, 4 chlorine atoms. And this illustrates how we need to be very careful with the letters when we write chemical formulas, because uppercase and lowercase can mean very different things. And so I chose this particular typeface because 1s, L's, and capital I's look different. So this is a capital I. When I write by hand, that's an L, and this is a 1. So some typefaces, you get that, and it could be any one of those 3. When I say Cl, I don't want that to be confused with Ci, which would be a different compound. Okay? So just watch out for that. We can write 3 different kinds of formulas, and which one we use depends on what kind of information we need to convey. There are empirical formulas, molecular formulas, and structural formulas. The empirical formula, empirical means from experiment. And so an empirical formula is found by doing an experiment, and we'll be doing one of those in experiment 3. It just gives the relative numbers of the atoms of each element. So, for example, hydrogen peroxide. The molecular formula for hydrogen peroxide is H2O2. That's an actual molecule, has 2 hydrogen atoms and 2 oxygen atoms. But the empirical formula is just the smallest ratio. So we can think of this 2 to 2. Can that ratio be made smaller? Yeah, 1 to 1 is the lowest ratio, right? So the empirical formula for hydrogen peroxide is HO. It just gives the relative numbers. It doesn't give us the actual numbers of atoms in a molecule. The molecular formula is better in that sense, in that it gives us the actual number. So here we have C4H8. That is a molecular formula. We could take that and write an empirical formula by looking at the lowest ratio. So 4 to 8, each of these numbers has a common factor of 4, so we can take 4 to 8 and reduce it to 1 to 2. This is the empirical formula. This is the molecular formula. For B2H6, this is a molecular formula. We can reduce that to BH3. This is the empirical formula. CCl4 is a ratio of 1 to 4. That's already the lowest ratio. And so here, the empirical formula and the molecular formula are the same. So how do we know, just by looking at a formula, whether it's empirical or molecular? Sometimes you can't tell. If you get something like this with the lowest ratio, it could be an empirical formula. It might also be a molecular formula. If you see something where it's not the lowest ratio, you can be certain that that's a molecular formula, because to find the empirical, you'd have to reduce the fraction or reduce the ratio. Any questions about that? Structural formulas give us more information. Here we use lines to represent covalent bonds. And this shows us how the different atoms are connected in an element, in a compound. Especially when we get into organic chemistry, exactly how the atoms are connected makes a big difference. And so you could have the same molecular formula, but it might be different compounds with different properties based on how the atoms are connected to each other. We use a single line to represent a single bond, a double line for a double bond, and a triple line for triple bonds. So the formula that we use depends on what we know about the compound and how much we want to communicate. The structural formula gives us the most information. The empirical gives us the least information. So here we're asked to write the empirical formula for these compounds given their molecular formulas. So what are we looking at here? We're looking at the ratio of atoms of each element, right? So this one has 5 carbon atoms to 12 hydrogen atoms. Can that be made smaller? No, because 5 and 12, the only common factor they have is 1. And so this is the empirical formula, C5H12. It's the empirical and the molecular formula. How about Hg2Cl2? We could reduce that to HgCl. How about C2H4O2? CH2O. So each of these subscripts could be divided by 2, giving us this formula. Any questions? We also represent molecules using models, and there are several types of models. The ball and stick model is one we often use. This represents atoms as balls or spheres, and the chemical bonds are represented by sticks. And then how those are connected gives us some information about the molecule's shape. We typically use the same color to represent a given element. I don't expect you to memorize these, but this is the color code that the book uses, and it's very common. White represents hydrogen, black is carbon, etc. And so the little drawings of water that we've seen have 2 little white balls and 1 slightly bigger red ball, and that's representing 2 hydrogens and 1 oxygen. We also have space-filling models. So this is an example of a ball and stick model, which is kind of like chemistry tinker toys. So we've got these little balls, and we attach them with the little sticks. Got my box of tinker toys here. This is an example of a ball and stick model. In a space-filling model, these are drawn so that the atoms more closely represent our best estimate for the actual space that they occupy. So this is the molecular formula for methane, CH4. The structural formula tells us that the hydrogens are each bonded to the carbon with single bonds. The ball and stick model gives us some information about its shape. The space-filling model, this is most like the actual shape of the molecule. Mm-hmm. That's an excellent question. So, do we know if the atom actually gets deformed like this when it forms part of a molecule? Yes, they do. And we'll learn more about that later, but their electron clouds overlap, and there are changes to the shapes. So this table just shows the different types of models and formulas for a few different compounds. Let's just look at this one here, glucose. This is blood sugar. The empirical formula, CH2O. This is the molecular formula. The structural formula shows us how the different pieces are connected. The ball and stick model gives us more information. The space-filling model looks more like a sugar molecule would actually look, and yet it has some limitations because when we look at a two-dimensional picture of this, we can't see what's on the other side. And that's the nice thing about the ball and stick model, is you can see through and see the things that are on the other side. So the different types of formulas and models have different uses, and we need to be okay with looking at all of them.